Software Engineering Radio Episode 19, Concurrency Part 2.
Welcome to a new episode on Software Engineering Radio. This is part 2 of our concurrency topic. This time we talk about synchronization and concurrency patterns.
In the first part of our concurrency episodes, we defined the terms a bit and talked about challenges like deadlock you have to deal with when you do concurrent programming. In this episode we will go a little bit further and discuss how to do synchronization and what concurrency patterns are there. A general remark on our concurrency episodes might be useful here. Please do not consider our concurrency episodes as a general encouragement to use concurrency for everything and everywhere. We would actually recommend to think a lot about when to use concurrency and how, because there's always an overhead associated with concurrency program, with threads, with multiple processes. So in the most common case of a single CPU hardware, you might not gain a lot from it. You get maybe a better reacting application, but you also lose some performance. So take care where to use concurrency and how to use it. Think about servers, there you have to use it, but always beware of the overhead associated with concurrency. So there are also some patterns or techniques out there to avoid concurrency and get applications that react as if they were concurrent, and one of this is reactive design.
Yeah, so in many cases, especially when only one CPU is involved, a reactive design using the reactor pattern can achieve quite high performance, as high as a concurrent design. The reactor pattern is used to dispatch events from multiple sources using a single thread. As long as the computation is short-lasting, this is a good design. But in case the computation after the arrival of an event lasts longer, you cannot circumvent that with a single thread and still be reactive. So you need multiple threads, and here you have basically two options, at least two options. First, use a concurrent design with one thread per event source, but that has its limitation. For example, imagine one source is quite busy where the other source doesn't emit events so regularly. In this case, you would only use one thread and the other thread would mostly run idle. So basically the threads are not shared across the event sources. A more advanced solution to that is using reactor in conjunction with a leader-followers pattern to achieve high scalability and best resource usage. But that is something we will discuss in part 3.
So let's get back to synchronization and concurrency. The first form we will discuss is the very simplest. It's a simple lock. And it's basically what we told last episode. It's about two or more threads sharing some common data, for example, variable or some resource like database connection. And the access to these shared resources needs to be protected. So in this case, you simply use some kind of lock and therefore control which of the multiple threads gets the resource. A more complex form of it is the monitor object. A monitor object is basically an object where every single method is protected by some lock. So you have to program in every method, or at the beginning of every method, you have to check if you have the lock. The object, the monitor object, has the lock. And after the method is completed, you have to release the lock. So the granularity is very coarse. You have always the whole object locked. So monitor objects are quite heavyweight, and of course it is at least dangerous to use monitor objects, because if you forget to get some lock or to release a lock, you have the problem that your monitor object doesn't work anymore. Especially cumbersome and error prone is of course the case of an error. You have to check that you also release the lock, otherwise the monitor will be locked forever. Another problem is you have to take care if you call another method from within your method. This can at least lead to deadlocks if your locks are not reentrant. And reentrant means if you as a lock holder have already the lock, you can also get the lock again and don't have to wait until the lock is released. Nevertheless, the advantage of monitor object is actually that it's very simple, very easy to use, very clean, and therefore it's the default, or it's a built-in feature of the Java language. It's the way how synchronization is implemented in Java, and therefore some of the problems don't occur there, of course, because you don't have to care to get the lock or release the lock. Another thing I want to mention about monitor object, of course you can use monitor objects as a mutex replacement. If you simply define an object that synchronizes, that gets the lock, you can use it to implement simple mutexes with monitor objects.
Yeah, the next pattern we want to discuss is scope locking. Scope locking has been documented in POSA 2, and scope locking helps you to actually release a lock again, because in many cases it is quite easy that a lock is not released, either by a programmatic error in that just the programmer forgot to put in a release statement, in that case of the if branch or the like, or an exception occurred and just a totally different execution branch is chosen. So scope locking encapsulates the acquire in the constructor and the release in the destructor. This way, as soon as you instantiate the guard who implements that, the lock is acquired, and as soon as the scope is left by any means, either because you just returned from that method or because an exception occurred, the destructor will ensure that the lock is released. Of course, this only works in programming languages that have a destructor, like C++. In Java, we have no destructor, and therefore, well, at least not in the classic sense. So in Java, this pattern just cannot be used. And another pattern from POSA 2 is active object. Monitor objects that we just introduced before are okay, but they are passive and they do not own any thread, so they must be driven explicitly by other threads. Encapsulating threads in so-called active objects that follow the active object pattern is a good idea for typical worker threads that accept input, perform an asynchronous computation, and then forward the results to any other object, potentially another active object. Active objects have typically an input queue, which is of course protected by a lock because it gets accessed by the client or the invoking thread, who hands over a computation request, and it is accessed, of course, by the thread of the active object. This way, the active object can accept multiple orders, multiple input data, while computing results based on the previous input. So the active object is reactive to the outside while it is still busy computing based on the orders previously inserted. Different strategies exist on how to handle the cases when the queue is full. Invoking client threads might block when the queue is full and just have to wait until it's empty again. The thread of the active object itself will typically block on the queue as long as it is empty. one brief discussion about queues. Queues often require dynamic memory allocations and synchronization. So this in turn can cause really measurable jitter, and in real-time systems this is the reason to minimize the number of queues used, especially in the critical path. And here again, architects should consider how to avoid queues, for example by using a reactive design.
One problem, if you have these active objects, the clients have to deal with the queues. They have to put in the requests in the queue, so that's not so problematic, but they also have to get the results from the computation back, and that's a bit, it's not very easy to do if you have to consider all this asynchronicity in your client code. So there is another pattern, it's called future, and a future is basically that your active object, for example, gives you a placeholder for the result and fills the placeholder for the result later on. You as a client of the active object don't have to deal with queues, you don't have to check. You just can use your future object as a normal result object from the active object and get the result out of the future object whenever you need. Of course, it could be that the result isn't computed yet because the active object wasn't fast enough, or the client was faster at this point. So you usually implement a future object with blocking get methods. If you want to take out the result of the future object, the get methods, or whatever they are called, block until the thing is computed, the result is computed. And usually future objects also have non-blocking check methods if you don't want to force your client to block for the result or until the result is computed by the active object. So such a design is only practical, of course, if only one result will be computed by the active object or by the asynchronous object, because if you have more than one result, you can't simply or you can't simplify the access for the client in that way as described in future object.
DoubleCheck locking is another pattern that we want to discuss in the context of concurrent designs. DoubleCheck locking is useful every time you do something lazily, every time you do something on demand. For example, in the case of lazy instantiation. One of the examples of lazy instantiation is the case of a singleton. Alex, could you explain what a singleton is briefly?
The purpose of the Singleton pattern is to ensure that there is just one instance of an object. So how do you do this? You usually write a method called instance, and in this method you check if the object is already created. If it is, you just return the reference or the pointer to the object. Otherwise, you create it and store the reference for later use. The Singleton pattern is actually a pattern where are some controversies about it, because it is not so different from using global variables, because usually you use it for a global resource, a resource that is only instantiated once in your whole program. And that's a problem, of course, because you usually have reference and dependencies spread all over your code to this global instance. So use the Singleton pattern only when appropriate and try to avoid it as far as possible.
So singletons basically erode your architecture. I know that Kevlin Henney, who I really value as an expert on object orientation, he can write episodes, he can write long articles on why singletons are such a bad idea. Still, they're an excellent use case for double-check locking. So, discussing about singletons, we should ask whether lazy instantiation and doing things lazily on demand in a concurrent design is generally a good practice or not. So I have no final answer to that, but generally I think it's a good idea to avoid on-demand actions, even if lazy acquisition in general saves you resources, because you would acquire them only when actually needed. So I'm kind of a bit torn what to recommend on this topic. But continuing with DoubleCheck locking, the problem is as follows. So in case of lazy instantiation, for example, you would need to check whether the resource or the object, the singleton to be instantiated, is already available. So if you do that not synchronized, then you can easily have the chance that just another thread did the same thing and instantiated the singleton or the common resource, and you have suddenly two singletons, two resources, and it would actually override the same variable, the reference to the singleton. So doing that in a synchronized way, you would just put a synchronized statement in Java across that critical section when you check for the existence of that resource and when you then instantiate the resource. But that really slows down your execution, because this check is always in the critical path. Every time you access the resource, you will use the so-called instance method, for example, of that of a singleton. You will be required to acquire and release the lock, which is quite slow. So the initial check for the existence of that resource singleton should be outside of any synchronized or locking statement. And here comes the DoubleCheck locking pattern. The solution is to do an initial check for the existence of the resource without synchronization, and only in the case when it's not existing yet, acquire the lock and check again whether it's already existing. Because while you waited on the lock, while you try to acquire the lock, somebody else might have created it already. So DoubleCheck locking helps you to avoid the overall expensive locking mechanism, and you will be required to acquire the lock only in the case when it's not existing yet.
Another warning here, please don't use DoubleCheck locking in Java, because it will not work. We will put a link on our website for an exact explanation why it is, but there is a fundamental flaw. Well, it's not a flaw, it's the way bytecode and virtual machine is actually designed in Java. There is no way to implement DoubleCheck locking pattern in Java without breaking in some very special situations. So don't use it. You have no chance to implement it. There have been a lot of threads in the internet on it, so check it out. It's dangerous.
Yeah, so with this we conclude our first introduction of some patterns in the concurrency domain. We will continue in part 3 with more advanced patterns. So in this episode we want to continue with some architectural considerations. The number of threads seems to be a critical topic and reason for some flame wars. For example, when I talk to the embedded people doing embedded projects, developing embedded applications for the automotive or automation domain, they tell me that historically it has always proved that they use as many threads as necessary. For every small responsibility they would introduce a separate thread. They would have queues between those threads, so the overall design looked like a mailbox system where the workers put orders for other responsibilities into their input queues, and at the end they ended up with dozens or even hundreds of threads. And the argument for that design, which they tell me, is that they could at the end fine-tune the system with priorities, assigning individual priorities to the threads and get the optimal best result. I don't believe in this design, to be honest. I think reducing the number of threads to a reasonable number, which in my opinion is somewhere below a dozen, is a good practice. Every time I was involved in such an embedded project and we designed the application with a reasonable low number of threads, we were still able to achieve the necessary real-time properties and the scalability and the performance, especially of the system. And the design often was easier, and it was easier also to track and debug the system, as I didn't have to check dozens of queue content. So Alex, what is your experience for the enterprise domain?
As you said, it's a very difficult topic, and actually I would recommend to move the decision how many threads to have to runtime. I would always recommend to make thread pools configurable and to actually make this threading strategy configurable, because it's nearly impossible to estimate or plan in advance how your application will run on the real production hardware, and usually the production hardware also changes over the lifetime of an application. People put in more CPUs or more memory, and therefore the whole thing behaves very different. So it's a good idea to not to design or to make a very fixed design front up and make these things like number of threads not configurable.
You just used the term thread pool. I guess that is something, an advanced topic that we will discuss in part 3, but briefly introduce what you mean by thread pool.
Okay. Threads are very expensive, not as expensive as processes as we discussed in the first episode, but still are very expensive to create. So a design pattern there is to have a pool of threads, and if you need a new thread, don't create a new one, just use one out of the pool and delegate the responsibility to do the job to one of the empty running or not used threads from the thread pool.
Okay, and afterwards you would have to release the thread again to the thread pool so that you could reuse it the next time.
Exactly.
So my personal opinion on how many threads are necessary in a system, for every part of the system that is highly interactive and needs therefore to be highly reactive, I recommend to use a separate thread. This is, for example, the case in the user interface design. Secondly, good argumentation or good reasoning is every time the control logic of a separated control flow of a concurrent design is easier to understand and maintain than a highly reactive design using the reactor. I would prefer the control logic being separated in a separate thread. And the third argument is use a reactive design with a thread pool in case you have long-lasting jobs. We will discuss this kind of design in the third part.
Yeah. Okay. Some of the recommendations I did for configuration of thread pools also are true for the priority stuff. I guess it's the only way to assign priorities to threads is to measure later on and then set the priorities for the single threads in your system. So it's a lot about measuring, in my opinion.
Yeah, assigning priorities is a quite difficult topic. In most cases I've seen that it's only done with some first estimations. Here Doug Lee gives some recommendations, for example, having for crisis management and interaction the highest priorities. Then for I/O and background tasks, so mid-level priorities, and the lowest priorities for the jobs that should run when nothing else is really necessary to be performed. But finally, at the end, the fine-tuning is almost always done by trial and error, basically. You try how your system performs, you do long-running tests, overnight tests, and then check the results and check the performance on whether you could achieve a better performance and better real-time properties by changing any of the priorities. A difficult and challenging topic is priority inversions, but that again we save for a later episode.
Mm-hmm. If we talk about the number of threads, we should talk also a bit about resources. If you develop in multi-threaded environments, you always have to take a look at where your resources are from and how scarce they are. I mean, if you have locks and there are operating system locks, there might be a number of locks your operating system can handle without a problem, and then there might be a number your operating system can't deal anymore. So same for a number of threads. Always take into account these resources might be very expensive, and that there are not an infinite number of locks out there if you have an environment with these constraints. So take the number of threads as a very important number in your consideration. It might trash your application completely if you have too many of them, or too fine-grained threads for too little things to do.
Yeah, so the general recommendation is to handle concurrency as an architectural topic, because it has a very strong influence on the architecture and at the end at the non-functional properties of your system. To sum up our second episode on concurrency, we would like to give the recommendation for general concurrent and network programming to read POSA 2. We put the link on our homepage as usual, and especially for Java developers, but also for non-Java developers. A good book on the topic is Concurrent Programming in Java by Doug Lee. This is one of my favorite books about concurrency. It describes step by step with many examples on how to do good design with Java and generally do good design in object-oriented applications. Alex, final word to say?
So thanks for listening. As always, we would be happy to get feedback from you to complete our concurrency series. The next episode will most probably deal with building highly scalable servers and advanced patterns in the concurrency domain. Thanks for listening.
Bye-bye.
This was another episode of Software Engineering Radio. The Software Engineering Radio team wants to thank Henning Pauli for providing the music, as well as Libsyn.com for hosting and bandwidth. For more information on the podcast, past episodes and feedback, go to se-radio.net.